All great movies deserve a sequel, and my nomenclature lectures are no exceptions. So if you loved my ionic nomenclature series, get ready for the spin-off series, Naming Binary Covalent Compounds, an original Dr. Kelly production with a capital randomly capitalized. First thing we need to do is we need to define what a covalent compound is. A covalent compound is a compound held together by covalent bonds. And a covalent bond, of course, is a shared pair of electrons. It's a pair of valence electrons that have an equal probability of belonging to the nucleus of two different atoms. Or has a significant probability of belonging to the nucleus of two different atoms. Why this definition of a covalent bond is important is that it means that covalent compounds' existence is much different than the existence of an ionic compound. We talked about how ionic compounds existed as crystals because that force of attraction could go all over the place in 360 degrees in three-dimensional space. Well, when it comes to sharing a pair of electrons, that can't happen. If two atoms are going to share a pair of electrons, the electrons they're going to share are going to need to stay between the two atoms. They can't go hither, tither, and yon all over the place. They got to stay located between the two atoms. That means that there is not an unlimited arrangement around a given atom. There's only a specific number of bonds an atom can form. Not only that, but the position of two atoms relative to each other is relatively fixed. Additionally, not only does it limit the number of partners an atom can have, but it means that when we look at the formula for an ionic compound, we're writing the formula for something that actually exists. That's so important, I'm going to write it down for you. Ta-da! Words magically appearing out of thin air. Ha ha! I do magic tricks as well as teach chemistry. The formula for a covalent compound represents the formula for a molecule as it actually exists. A molecule is the simplest unit of a covalent compound. Not too magical. Can't seem to get my writing right. But at any rate, ta-da! Words magically appearing before your eyes. What can I say? I not only do chemistry, I do magic as well. Although some people say that chemistry appears magical. Some people say that the chemistry I exude is magical. But at any rate, the formula for a covalent compound represents the formula for a molecule as it actually exists. A molecule is the simplest unit of a compound. What do I mean by that, and why am I making such a big deal out of that? Well, let's start with what I mean by this. What I mean by this is that when I write the formula for water, H2O, this represents water as it actually exists. Water actually exists as two oxygen atoms, as one oxygen atom attached to two hydrogen atoms. When you drink a glass of water, you're drinking a collection of little molecules, and each one of those little molecules consists of one oxygen atom connected to two hydrogen atoms. That's how water actually exists. When you turn on your stove and you light natural gas, you're lighting methane, one carbon connected to four hydrogens. That's how it actually exists. That gas is a collection of little molecules with one carbon attached to four hydrogens. You're like, well, duh, what's the big deal here? The big deal is how this differs from ionic compounds. Remember when we talked about ionic compounds, we said that the formula didn't represent something that actually existed. When we wrote the formula, sodium chloride, we said there wasn't any single sodium and chloride ions out there floating around having a party by themselves. Instead, it was just a ratio of things in a crystal when we were dealing with ionic compounds. When we wrote the formula for an ionic compound, we were just writing a ratio, not something that physically existed. For covalent compounds, that formula represents something that physically exists. Not only that, but the formula, because it represents something that physically exists, it's not a ratio. The fact that it's not a ratio is important. It means that for covalent compounds, because the formula for a covalent compound doesn't represent a ratio, but represents something that actually exists, it means that covalent compounds, that when you're dealing with covalent compounds, there can be multiple combinations of just two elements. One of the easiest to think of it is nitrogen. I'm sorry, I am so excited I'm losing control of my ability to speak here. I'm beside myself. The strange thing is I'm also talking to myself beside myself. But at any rate, nitrogen and oxygen alone can form all sorts of combinations. Each one of these combinations actually exists. And because each one of these combinations actually exists, we have to have a nomenclature system that allows us to name these compounds as different compounds. That simplistic system we used for ionic compounds won't cut the mustard anymore because it doesn't allow us to name all these. Pardon me, now I got the burps. It doesn't allow us to name each one of these compounds individually. So we have to develop a system that does. Fortunately, when I say that the system for naming ionic compounds was simplistic, that doesn't imply that this system's any harder. Matter of fact, most students find the way of naming ionic compounds much, much easier. To name an ionic compound, and let's walk through the process here. Let's name an ionic compound that you guys already know the answer to. My guess is you can already name this compound without me walking you through the rules to name it. But we have this compound here. The first thing we're going to do is we're going to verify that we have a covalent compound. You will have a covalent compound when you have two non-metals bonded together. Now, the other rule for when you have a covalent compound is the pinky out rule, the highfalutin, you're having a cup of tea with the queen rule is the electronegativity difference between the two atoms is less than 1.9. Huh? What's electronegativity? If you're in my class, we've covered it in a different lecture. If you're not in my class, don't worry about it. Because as I said, that's the very formal rule. it's much easier and much simpler, and it's what everybody does, is they simply say that you have a covalent compound whenever you have two nonmetals bonded together. So if you have a covalent compound, that means you have two nonmetals. Your first step, once you've verified you have a covalent compound, write the name of the first element. So in this case, our first element's carbon. Second step, write the name of the second element with the suffix IDE. So just like we did with ionic compounds, we take that second element, we drop the last syllable and add IDE. So our second element here is oxygen, so oxygen is going to become oxide. So we have carbon, then we have oxide. Then we've got one last step, and that's denote the number of each atom using Greek prefixes. Omit the prefix mono on the first element but never the second. Oh wow, that's a loaded third step, huh? Denote the number of each using Greek prefixes. Greek prefixes? What Greek prefixes? How do we suddenly get into the Greeks? I thought we were taking chemistry, not history. Where did this Greek prefix business come from? We're going to use Greek prefixes to denote the number of each atom present. And these Greek prefixes, and I've got these rules and the Greek prefixes typed for you on the next slide. So if you can't read my sloppy handwriting, chillax, you'll see them in a second. But these Greek prefixes are as follows. The prefix mono equals 1. You kiss the one wrong person and you get mono. Di is 2. Do not confuse di with bi. Bi means the presence of a hydrogen ion. Di means 2. Then tri. Everybody's had a tricycle. Tricycle. I want to ride my tricycle, right? Tricycle. 3 wheels, tricycle. All right. Tetra is 4. Everybody's played the game of four-sided objects, Tetris, on their cell phone. Penta, everybody knows a pentagon is 5 sides, just like everybody knows a hexagon is 6 sides. Hepta is 7, don't have a good one for that. Octa is 8, octopus. Nana and 9 both begin with the letter N. And then deca and 10 years in a decade. See, boom, you've memorized those Greek prefixes right here, right now, no problem. So if we look at our molecule here, we have carbon and oxygen. So we have carbon oxide, and now we need to denote the number of each. We have 1 carbon. We would use the prefix mono, except carbon is the first element. By convention, you never use the prefix mono on the first element. You do, however, have to use it on the second element. So just to name another compound real quickly, This compound, just CO, would be carbon, and then you have oxygen become oxide, and you have one carbon, you omit the prefix mono, but you have one oxygen, so you include the prefix mono for oxygen. So this would be carbon monoxide. Over here, however, in our original example, we have carbon, and we have one, so we omit the prefix mono. We have oxygen, and we have two of them, so we use the prefix di. So it's carbon dioxide. Chemistry's easy, life is hard, right? I had to work hard to come up with all those rules just to make this sound impressive so that you'd pay me for my services. All right, let's take a look at another example. Okay, here are the rules for naming a covalent compound, and this is part of that flow chart that you saw big if you've been doing my nomenclature series with me, my nomenclature trilogy, the best trilogies in Star Wars. If you've been working through your videos for me, this is part of that larger chart. We have an ionic compound. When we say, is the first element a metal or ammonia? No. That means we have a covalent compound, or two nonmetals. We write the name of the first element, write the name of the second element with the suffix IDE, and we use the Greek prefixes to denote the number of each. So let's do another example here. We have that staring at us on an exam, and right off the bat I've thrown you a little bit of a curveball because I have boron, and boron's a metalloid. Generally you treat metalloids, or at least I always treat metalloids, as covalent compounds by default. There are examples of metalloids forming ionic compounds, however, though. So watch that one, but in this scenario, if we subtracted the electronegativity differences, we'd find it's a covalent compound. So we write the name of the first element. Whoops, that's not going to show up, is it? We write the name of the first element. Write the name of the second element with the suffix IDE, so chlorine becomes chloride. Use prefixes to denote the number of each. We have two borons, so diboron. We have four chlorines, so tetra. So it'd be diboron tetrachloride. One good example deserves another, is what I've always said. Oh, really? Was that a good example? You threw a metalloid at us, violating the first rule you're trying to do. Yeah. Everybody's a critic. Let's take a look at one of our nitrogen-containing compounds. All right, we have two nonmetals, so we have a covalent compound. So we write the name of the first element, nitrogen. We write the name of the second element with the suffix IDE, so oxygen becomes oxide. We use our Greek prefixes. We have two nitrogens, so it's dinitrogen. We have five oxygens, so, well, I'm just going to make a mess of it there. So it's dinitrogen pentaoxide. Chemistry is easy, life is hard, yes? Just to make sure this horse is dead, let's do a couple more examples. All right, we've got this one. We have two nonmetals, carbon and fluorine, so we write the name of the first element, carbon. We write the name of the second element, fluorine. Fluorine's going to become fluoride. We have four fluorines, so it's carbon tetrafluoride. Two nonmetals, phosphorus and bromine. We write the name of the first element, phosphorus. We write the name of the second element with the suffix IDE. Denote the number of each, so it's phosphorus pentabromide. Quick comment, something fun to talk about at parties. Why is it that we admit the prefix mono on the first element but never on the second? Here's the reason. If I want to talk about this compound right here, I call it carbon monoxide. But if I want to talk about all the compounds that contain carbon and oxygen, all of them in the entire universe, if I want to talk about all the compounds that can be made from only carbon and oxygen, I refer to them as carbon oxides. So that winds up being a sort of family name, if you would. Whereas this refers to just the individual compound. This refers to the family of compounds. You see this a lot. You see the family names used a lot with sulfur and nitrogen compounds. Acid rains died away as a big, hot environmental issue. I don't see people protesting in the streets it anymore like they used to. But SOx and NOx were major contributors to acid rain. Right? All these compounds contain only nitrogen and oxygens. So they're nitrogen oxides. All of these guys. However, if I want to talk about just that compound, right there, that compound is nitrogen monoxide. So that's the reason we have to include that mono on that second element there. Just in case you were curious about that. And I knew that you were. Alright, let's keep going here. We haven't gone in reverse. Know what we also haven't done? I haven't told you yet to watch Arrow on the CW. You should be watching Arrow. It's a really awesome show. Why don't you write down the word arrow? Everybody should write down the word arrow. I hope you're writing down the word arrow. Alright, let's go from the name to the formula. Going from the name to the formula is so ridiculously easy for these guys. You see that looking at you on an exam. You see a Greek prefix right away. That makes you happy because it lets you know you have a covalent compound. You also see you have two nonmetals, so you know you have a covalent compound. So you write the elemental symbol for each, and then you use the prefix to tell you the number. Di, so 2 nitrogens. Mono, so 1 oxygen. Boom! You're done. Drop the mic. Alright. Sulfur hexafluoride. Sulfur hexafluoride. We have sulfur. We have fluoride, or fluorine. We have 6. So it's hexa, nothing there, so it must be 1. So boom, we're done. And fun. No way I'm stopping now. Tetraphosphorus, and watch my spelling of phosphorus. I did actually live overseas for a while, and I lapsed into the Queen's spelling. Ah, good. I'm on the right side of the pond at the moment. All right, tetraphosphorus. Trisulfide, tetraphosphorus trisulfide. So we've got phosphorus, we have sulfur, we have tetra, so we've got 4 phosphorus, we have 3 sulfide, so P4S3. Chemistry's easy, life is hard. There's nothing I can do to make this difficult. Alright, that's it for naming simple binary covalent compounds. Thank you for joining me, and see you here next time. Same bat time, same bat channel.